Everybody can see. So thank you for the kind introduction. Today I'll be talking about, yeah, exactly as you said, about muons, about quantum effects of muons, basically how they can help us uncover non-trivial things about magnets, especially, and focusing mostly on the development of the technique, basically how to make it more quantitatively correct. Okay, so this was work done at my postdoc at Durham University under the supervision of Tom Lancaster and Stuart Clark, in collaboration also with the ISIS facility in England near Oxford, where they have a muon source, an accelerator for that, with Francis Pratt and Stephen Cottrell. Okay, so firstly, for some motivation and introduction about why we should care about muons. So muons are a very powerful technique for measuring internal magnetic fields inside material. So very weak magnetic fields and fields that are fluctuating at interesting frequencies that other techniques cannot really access well. So the technique works like that. So we have an accelerator producing a muon beam. We direct the beam towards our sample where the muons stop somewhere inside the sample. Then they precess around the internal fields in the sample. And then once they decay, they emit a positron. And due to parity violation, this positron is emitted mostly in the direction of their instantaneous spin, so of the muon spin. So if we track the number of positrons that are emitted in the backward detector versus the forward detector versus time, we can see how the muon spin precesses in internal fields inside the sample. So for example, if we see such a signal for the difference, so the relative difference between the forward and backward detectors, a nice cosine, we know that the muon is experiencing a single field that is static on the muon time window. So other possibilities are we get the following universal shape, the Kubota-Yabe shape, which indicates that we have static fields inside a sample, but they are random. So because we have a muon beam, we send in many muons one after the other and collect statistics on the results, on the resulting positrons. If the fields are random, then they cancel after long times, leaving a so-called one-third tail. On the other hand, if, for example, the fields are not static, but dynamical, if they're fluctuating with frequencies around the muon time, so around megahertz to terahertz frequencies, we see a different kind of polarization. And from this, we can immediately say that the fields are not ordered inside a magnet, they are fluctuating, and we can quantify the fluctuation frequency of these kinds of fields. So it's a very powerful technique for measuring very small magnetic fields in samples. And it's very interesting because it covers a range of frequencies that's mostly inaccessible to other techniques. So we have NMR, for example, or AC susceptibility, which measure much lower frequencies. We have neutron scattering and inelastic neutron scattering, which can measure excitations at much higher frequencies. But there's a gap that's not covered by almost any other technique. And it's in this gap that many very interesting quantum magnetism effects live. So it is a gap that's very well worth exploring, and MUSR is basically the only technique that can give us information there. So for example, some of our recent papers that relied on having MUSR as a technique to measure the fields inside a sample were, for example, proving that a material is actually a quantum spin liquid, so that its ground state is not magnetically ordered, but it's fluctuating and it's highly entangled. Other results were, for example, that materials have magnetic impurities that are non-trivially coupled with the surrounding spins. Then a paper proving a spin-on Kondo effect, where we have an analog of the Kondo effect known from metals, but inside electrical insulators, where the coupling is instead to spins inside the system, so local spins instead of itinerant spins. And for example, we can study topological magnetism as well, so excitations of large topologically protected vortices of magnetization. So none of these papers would be possible without MUSR, really. So even though it's a very nice technique, it has some issues when it comes to being quantitatively precise sometimes because of the muon site problem. So once we have our sample, which is usually a crystal, like what is shown on the right-hand side here, a unit cell of a crystal, how do we know where the muon will sit inside this crystal? So the muon gets into our sample and stops very quickly due to electrostatic forces on the order of picoseconds or less. And then it very slowly, on the order of microseconds, precesses around the internal fields. So, but we don't know where it's going to stop. So we don't know which magnetic fields we're actually measuring. So how far away are we from certain types of ions in our crystal? So this kind of problem has been a problem of USR for a very long time, but it's been recently solved in the last 5 to 10 years, almost completely using ab initio DFT calculations. So these are electronic structure calculations that can tell you how the electrons behave inside crystals without assuming anything. So from first principles, basically just putting in the atoms and letting the code calculate where the electrons are and where the muon would like to sit in the crystal. Okay, so just a few words about this technique. So our goal is to find the muon and of course nuclear positions that minimize the total electrostatic energy between the muon and nuclei, and also any electron energy. So the electrons have to adapt, so they chemically bind actually. Nuclei together, they can also chemically bind the muon to the crystal. And the way they configure themselves, together with Pauli exclusion principle effects and things like that, so correlation effects, that gives some total energy. And when this energy is minimized, then we get a stable situation. So we're trying to find basically where does the muon chemically bind inside our crystal lattice. Basically, that's the problem. And that's a problem that's well known from quantum chemistry, a problem of predicting crystal structures. Basically, this time it's predicting impurities in crystal structure, where they should occur. So the standard problem with this is that the electronic wave function has a number of parameters. So it's if you have n electrons in a crystal, then we have 3 n-dimensional wave functions. That means we have to, so we have for every pair of 3n numbers, we have to specify one complex amplitude of the wave function. This is intractable in practice. This is completely impossible to write down, as Dirac already noted in 1929, when he said that the exact application of these laws, meaning the laws of quantum mechanics, leads to equations much too complicated to be soluble in general. Yeah. So just to illustrate the problem, for example, if we had a simple molecule of benzene, so C6H6 with 42 electrons, that means the electronic wave function has 126 dimensions. If we discretize each coordinate on a 10 by 10 by 10 grid, which is quite coarse actually, then to specify the amplitudes of the wave function, one would need 10 to 3n, so 10 to the power of 126 different, in principle, different complex numbers. This is vastly more than the number of atoms in the observable universe, which is about 10 to the 80. So the wave function, even though it's a nice idea, and if we get some nice example where we can write down some analytical way of expressing it, it's in principle a nice idea, but actually writing down the general wave function from a general Schrödinger equation is completely impossible in practice. But there are ways around it. We don't necessarily need to write down the electronic wave function to find the energy of the electrons. So this was the development of DFT, basically, which won the Nobel Prize for chemistry, because it's a quantum chemistry technique, in 1998. So Hohenberg and Kuhn proved that if you have electrons interacting through Coulomb interactions inside some external potential generated, for example, by the nuclear positions, then any observable that we might even in principle want to measure on the electrons depends uniquely and only on the electronic density, which is more or less a classically accessible thing. So it's a function of only 3 dimensions. So x, y, and z. For every point in space, we have to specify the probability density of finding one or any electron in that small volume of space. And that's in principle enough to reconstruct back, that's what Heisenberg improved. That's enough to reconstruct the whole Hamiltonian that has this density as the ground state density. And from the Hamiltonian, in principle, everything else could be calculated. So for example, the electronic wave function, all the excited states, all the energies of the excited states as well, everything is ultimately determined by just this electronic density, which is a function of only 3 parameters. This is kind of non-trivial, I would say, and it is the basis for DFT. So a theory where we want to express the total energy of the electrons inside an external potential as a functional of the electronic density of this function of 3 parameters. This has 2 parts. One is the external nuclear potential, which is trivial to write down, and the other is the so-called universal functional. So something that gives you everything else. So all the electronic correlation effects, everything that's exchange effects and things like that. So, and Coulomb screening and everything. So this F part is universal. It doesn't depend on the coordinates of the nuclei, but this functional is, it has a slight problem in that we don't know what it is. So before we had the electronic wave function, which we couldn't write down, but we could write down at least the equation it satisfies. That's the Schrödinger equation, even though we can't actually solve it in terms of the wave function. Now we have some function that we can write down, this 3-dimensional density, but it depends. So the energy that we try to minimize depends on a functional that we don't know. So we don't know what equation this density actually satisfies. But there are good approximations to it that work reasonably well for almost all cases of experimental relevance. So it is an approximate technique just because we don't exactly know what this F is. There are certain properties of it that are known, for example, that it's non-analytic, that it has some derivative discontinuities and things like that. This is a highly non-trivial functional. It captures all of quantum mechanics ultimately, but there are good approximations that work for example, crystal structures and molecular structures. So using these approximations, people now had a method of calculating the structure of crystals, the structure of molecules, everything that they wanted to. So this is the number of papers written that rely on DFT over the years. We see a huge growth, starting even before the Nobel Prize. And there are now, by now, a lot of popular codes that you can basically just install, usually in a supercomputer, and run like within minutes. If you give me a crystal structure, I can run the first calculation almost immediately. And as a result, you get any electronic observable in principle that you might want. I mean, within reason. So for example, the electronic density, the spin density, binding energies, things like that. Okay, so it's such a popular technique that it's used almost everywhere now, including in physics. One example is our recent paper where we used it, for example, to calculate magnetic exchange couplings from just the crystal structure. So the exchanges between spins. Okay, so going back to the muon side problem, we want to know where the muon would sit in this crystal lattice to minimize the total energy, total configurational energy. And this is given by DFT, which identifies 4 distinct muon sites in this crystal. And if we didn't know that there were 4 or how far they are from the relevant ions in this crystal, we would have a very hard time interpreting the experimental spectra because there are just a sum of 4 contributions, 4 separate contributions from each of the muon sites. We also can calculate distortions of the crystal lattice because the muon is there. So if this is the pristine structure. If you put a muon in, it moves the atoms. So we locally distort crystals as well. We don't just measure them passively using QLCR. But now that we know how the crystal is distorted, we can correct that or take this into account when interpreting experimental spectra. So we can make the method quantitative in QLCR. There are just a few assumptions here. So what we assumed that the muon and all nuclei as well were classical particles that were at rest at their final positions. The only thing that was quantum mechanical here was how the electrons move around these nuclei, how they bind them chemically together. But we still assume that the nuclei are fixed in place and classical. Do we have any justification really for this assumption? That's the question. If we look at hydrogen, for example, and hydrogen bonds, we don't. So one example that's well known is hydrogen bonds are substantially strengthened, the strong ones, and the weak ones substantially weakened due to quantum effects, because the hydrogen in such a bond actually delocalizes either along the bond in strong bonds or perpendicular to it in weaker bonds. And this on average either increases the binding energy or decreases the binding energy. So at least for hydrogen, it's now well established in quantum chemistry that such quantum effects are very important and we cannot neglect them. So, I mean, the changes in the strengths of bonds are 30–40% even, so very big effects. The other thing is quantum tunneling. For example, in ice, if we increase the pressure, external pressure, we get a transition from where the hydrogen is close to a single oxygen to where it's tunneling between two potential minima, and then finally sitting at just a single unique potential minimum at very high pressures. So these are different types of ice. They have quantum mechanical tunneling of hydrogens within them. The problem is muons are even lighter. So if a hydrogen is the lightest atom that we want, like the lightest normal element that we want to have in a crystal, muons are 9 times lighter than them. So we expect them to have much stronger quantum effects, much stronger effects of quantum delocalization, tunneling, and things like that. But remember, we previously assumed that there were classical particles at rest in the final position. This cannot be justified. They cannot be point particles in many cases, actually. So it's because muons are very light, they are not classical, and we expect strong delocalization. Large effects of 0-point energy, so we expect about half an eV of 0-point energy, even though the differences between the different sites where the muon would like to sit in the crystal that we calculate using classical assumptions are less than half an eV. So some of those muon sites that we calculate using DFT might become unstable. Some might merge together into a single site just because of 0-point energy effects. There might also be quantum tunneling between the sites, even Bloch waves. So sometimes a muon can produce a coherent Bloch wave across the whole crystal if the potential that it finds itself in is very shallow compared to its 0-point energy. This has also been observed experimentally. And in disordered systems, you might get effects of Anderson localization and things like that. So our goal in Durham was, so on my postdoc, was to develop some ab initio methodology for treating muons as quantum particles as well. So to aid in the interpretation of MUSR experiments. Okay, so overview of this talk. The main part of the talk is we'll look at a model system, in this case solid nitrogen. We'll introduce some standard approximations that people have developed to approximate the full quantum mechanical picture. And then we'll go to the full quantum mechanical treatment using PET integral molecular dynamics, which is a very specific technique that's now becoming quite well established in the field of quantum chemistry, actually, but not yet in physics as much, especially not in MUSR. And then I'll compare the results with the experiment. So our model system is solid nitrogen. So at low temperatures and low pressures, the structure of nitrogen, it looks like this. This is a supercell, 2x2x2. These are N2s bonded together with extremely strong bonds. So these are the second strongest bonds in nature. The only stronger bond than the triple nitrogen bond is the oxygen. So there's the monoxide bond. That's the only one that's stronger. But between the nitrogens, we have extremely weak dispersion forces, the van der Waals dispersion forces. And if we put a muon inside such a crystal, experiments have claimed to show strong quantum effects, so of tunneling and Bloch waves and things like that. But there was no ab initio theory to support the conclusions, really. So I started with this crystal, and if we put a muon inside here, a muon in this case is a positive particle in our case. So we're working with antimatter actually. So it's an anti-muon technically. So it's a positive muon that we implant in there. and it acts like a lighter isotope of hydrogen, of ionized hydrogen, I guess. From the point of DFT, there's no difference in the external Coulomb potential if it's a hydrogen, a deuterium, or a muon that's producing it. So this chemically binds actually two nitrogens together into a linear complex with a total charge of +1. And this induces electric dipole charges, electric dipoles in the neighboring nitrogen molecules in the crystal. But because they're very weakly bounded together into the crystal structure, they can reorient strongly towards the muon complex, N2 mu plus N2 complex. So we basically get something that could be described as a polaron around the muon, a charged polaron. So the crystal deforms strongly because of the muon. Now, in this complex, people have studied this thing before, but outside of a crystal structure, just on its own, but using different kinds of approximations. So one was adiabatic single particle potentials. I'll explain what those are later. The other was harmonic approximations. But the conclusions varied a lot between the different approximations. So some predicted a very flat potential for the muon that is moving in between the nitrogens. Others found a single, and others, again, a double potential well with tunneling. But none of the studies before introduced crystal effects. So the fact that we have a lot of nitrogens around the complex that reorient together, so move together with the muon. Okay, so this is where we started. So what are the standard approximations that people make when studying quantum muons? We can divide them along two axes. One is either they consider just some effective single particle potential, so something that depends only the coordinates of a single particle. These are the so-called adiabatic approximations that can reconstruct the full potential, but just assuming that a single particle produces it. The other possibility is multi-particle potentials, either with harmonic binding between the different nuclei or muons. So these are phonon-based methods, because phonons are the harmonic expansion of internuclear forces or interionic forces. And finally, the full method for enharmonic multi-particle effects is PIMD, which I will describe lastly. So let's start with the adiabatic approximations here, the single particle enharmonic approximation. So what we do in practice, this is a very simple technique to implement. So we just calculate the DFT energy, so the electrostatic energy plus the electron energy, for fixed displacements of our test particle, in this case a muon. So if the muon starts here, we can move it along some direction. This is inside the crystal though, and calculate the energy for each of the muon positions without optimizing the geometry in any way, just calculating the total energy. So if this test particle is very light, then this is probably the correct approximation, because if a light particle finds itself surrounded by very heavy molecules, then it's going to be moving much faster than the molecules can manage to follow. So this should be the correct approximation, more or less. If, on the other hand, the test particle is very heavy compared to the natural vibrational frequencies of everything around it, then we have to take into account that if it moves a bit, then the crystal structure is going to adapt almost instantaneously. That's the other extreme limit. So if you move the muon, the nitrogens move around and form chemical bonds and things like that as well. So either we calculate the single point energy for each displacement, or we relax the whole crystal structure for each displacement. And these are the two limits that should be correct in the limit of extremely light or extremely heavy muons. What we neglect is all the multi-particle dynamical effects at intermediate masses, where the natural frequency for the muon vibrations is the same as the natural frequency of N2 vibrations, for example. That is not described by the single particle approximation. In any case, so this is a very popular technique, very simple. I mean, popular amongst the community that's even bothering to calculate the quantum effects. So this is a very new area of research, actually. So it's if the muon size problem was more or less solved within the last 5 to 10 years, the quantum muon problem is being tackled for the last 3 years, I would say, something like that, 3-4 years. Okay, but it's not been solved yet. So on the right-hand side, we get this single particle potential. So on the x-axis, we have the muon offset. On the y-axis is the effective potential, but in a square root scale. So be careful. Anything that looks linear on this graph is actually a parabola. So it's a harmonic potential. Anything that's linear describes a harmonic potential. So we see that for small displacements, the energy is mostly harmonic, but then it starts to deviate. There are anharmonic effects at large deviations of the muon. So this is under the assumption of a fast muon, where the nitrogens are completely stationary. The other limit is for a slow muon, where we relax the whole crystal structure around each instantaneous muon position. We get this orange potential, which is much shallower. We see that even compared to the thermal energy, which is usually much lower than the 0-point energy, even the thermal energies, the two approximations differ a lot in terms of what what one would anticipate the muon wave function spread to be. So how far it spreads. This discrepancy doesn't look promising for us. If it depends that much on whether the nitrogens moved or not, once the muon moved, we might expect that we have to do more than a single particle approximation here, that we have to actually take into account that muons, the nitrogens have their own vibrations as well. But okay, we're not completely sure. In the most optimistic version, we might say that, okay, maybe one of the two limits is correct, the other is wrong. But because they're different, we don't really trust either at this moment. Okay, the other option is going to multi-particle approximations, but with harmonic interactions between the different ions or nuclei. So this is also relatively easy to implement, a bit more computationally intensive though. So we calculate the DFT phonon spectrum at the gamma point with a muon inside the crystal. That's the first step here. What this means is we calculate the vibrational frequencies of the crystal, assuming it also has a muon that can move in a correlated fashion together with everything else in the crystal. We calculate phonons, basically. We assume a harmonic interparticle potential, and we assume, so we don't have to assume, we know that the muon eigenmodes should be completely flat in K-space. That's because the muon is a localized particle. It should have no dispersion over neighboring unit cells. The relative phase between the unit cells shouldn't matter because there's only a single muon inside. Okay, so once we calculate the phonon spectrum, we take the top 3 frequency phonon modes because the muon is supposedly the lightest thing inside the crystal aside from electrons. Those should correspond to the muon motion. And then we know exactly that the 0-point energy is h bar omega over 2 for each of those modes. And the modes describe correlated dynamics, where the muon moves on the same time scale, possibly, as the nuclei. So it goes beyond single particle approximations in that sense as well. What it does neglect, though, is any anharmonic effects, which we previously got for free. But in parentheses, we know those to be very important for hydrogen, in hydrogen bonds, for example. So even though this looks like a sensible technique, a multi-particle technique, we know that it must fail at least for hydrogen. It probably does fail for muons as well, which are even lighter. In any case, that's not the only thing that we neglect. We, of course, also neglect any effect of multiple potential minima. So any tunneling, Bloch waves, and things like that also aren't described by this. In any case, we can at least try to calculate the effective potential for the muon from this. This is the dashed line here. As we see, it's completely flat in this scale, meaning it's completely harmonic by construction. The advantage here is that we have exact solutions for both the the correlated wave function of the whole system, and also for the energies and everything else we want. For example, if we plot on here the harmonic 0-point energy, we see that the muon wave function spread should be about 0.3 angstrom each side of the muon, so of the equilibrium position. The problem here is that 0.3 angstrom away from the classical equilibrium position means that we enter the adiabatic, so the enharmonic regime. So the adiabatic approximation with n-harmonic effects gives a very different energy from this harmonic approximation at these kinds of offsets. So we expect actually that this, even though it's multi-particle, the harmonic part is problematic here. It's the muon effective potential is not harmonic, likely. So we suspect that phonon-based methods also fail. We're not sure about either of those at this point yet, but let's just continue slightly more with phonons. What if we let the muon mass vary? So what we're trying to do is basically calculate isotope effects for the phonons, I guess. So at the experimental muon mass, we get some frequencies, but if we vary the mass of the muon, we can calculate easily the whole spectrum. So all the eigenmodes of a crystal with a muon n. We see features that are recognizable. For example, the crystal lattice at very small frequencies. This is because the two N2 molecules have very weak nitrogen bonds, so van der Waals bonds between them, meaning that the natural frequency for crystal lattice vibrations is extremely low. But because the N2 bond is extremely strong, the intramolecular vibrations have a very high frequency, actually. And aside from nitrogens in crystal lattice modes, we get 3 extra modes: a longitudinal mode along the N2 mu N2 complex, and 2 transverse modes, where this color scale here shows how much the muon moves inside a single mode. So the red modes are the muon modes, the blue modes are nitrogens. The problem is that at the muon mass, we see that there's hybridization between the longitudinal mode and intramolecular vibrational modes of single N2 molecules. Because there's hybridization, that means there's correlated N2 mu plus N2 motion. So it's definitely not a single particle type of motion. The muon is not moving on its own. There are more degrees of freedom that are relevant because of its specific mass or low mass. Okay, because we see this correlated motion, this hybridization of just what the muon would like to do inside an external potential with the vibrations of N2 molecules around it. This correlated motion means, as I said, that single particle approximations must necessarily fail because they completely neglect this effect. They completely neglect that more than a single particle is moving, or more than a single particle's degrees of freedom are relevant. But moreover, we also see that there's quantum entanglement between the muon and the nitrogen positions. How do we see this? This is a very simple proof. So if we have 2 particles with a separable wave function, and we look at the expectation value of the correlation of the 2 positions, so we look at the deviation of the first particle from equilibrium times the second particle from equilibrium. If the wave function is separable, this separates into 2 expectation values, which are by definition 0. So these are deviations from equilibrium. On average, they should be 0. On the other hand, if we see that there's non-zero correlation, we can invert the above deduction and say necessarily the wave function that produced such a correlation must be quantum entangled between the 2 particles. It's not a separable product of the 2 particle wave functions, the 2 single particle wave functions. So because phonons predict that the muon and nitrogen positions should vary in a correlated fashion, that means in the ground state wave function of the muon and nitrogens is quantum entangled necessarily. It's not classical at all. Okay, we'll return to this actually slightly later. So we see that single particle approximations must necessarily fail. There's quantum entanglement between different particles. We see that there's correlated motions between them. There's more degrees of freedom than a single particle can describe. So single particle approximations are completely out. We still suspect that phonons are not correct either because there are probably highly relevant and harmonic effects that that we have to take into account that phonons don't. But we'll see that actually, if that's the case, by moving to this final, the quadrant here, and harmonic multi-particle effects. So the most general kinds of effects. So this is where path integral molecular dynamics enters the picture. Okay, so ideally, we would like a fully quantum and anharmonic treatment of both muons and the neighboring nuclei, because they are quantum entangled, they're not separate. The problem is that the nuclear wave function, again, if we have n nuclei, this is a free n-dimensional wave function. And as we saw before for electrons, this is completely intractable. We cannot write down the wave function. Even if we know precisely what the Schrödinger equation is, and it looks very simple, we cannot ever write down the wave function in terms of its individual components, just like this. Either there are some tricks how to construct it, or we just cannot. The question is, can we avoid using the wave function at all? So continuing this thread of reformulating the problem if you don't like the answer, is can we avoid solving the Schrödinger equation? There is a solution. It's called PET integral molecular dynamics, as I already mentioned, and it is becoming more and more popular in quantum chemistry. So, for example, this first reference, the latest one, the title of it is something in the sense of quantum nuclear effects are becoming mainstream. So with the advent of huge computational capacity in supercomputers that's increasing year by year, these kinds of calculations, which were previously too hard to do in practice, are now becoming feasible and are more and more routinely solved on supercomputers. Okay, so how does PET integral molecular dynamics work? So this is just a short foray into some theory, but you don't have to understand or track every equation here. This is just to give you an idea that this is not some kind of black magic, that this is actually sensible. Okay, so in quantum mechanics, we are interested in thermal averages. So this is defined as a trace of some observable times the exponential of the Hamiltonian operator. The Hamiltonian operator is, in this case, a kinetic part plus a potential part. And this exponential cannot be easily solved in general. But we can decompose it using Schroeder decomposition. So we take alternating steps of a bit of kinetic energy and a bit of potential energy, and we repeat this p times, with p going to infinity in principle. And we then plug this in to our traces above. If we assume that the observable that we're interested in depends only on position, this is not strictly necessary, but it simplifies things, and expand everything in a positional basis, then we get the following equation. So some kind of multiple integral times the observable at some point, times some expectation, some matrix element of these two exponentials. The advantage here is that the two exponentials are separated, and these matrix elements are exactly known. They don't have to be approximated. The only approximation is that p must go to infinity for this to become completely exact. You might have seen this before if you've taken quantum field theory classes or something like that. This is basically an alternative way of defining statistical mechanics through Feynman PET integrals. Basically, this works the same way. But okay, in any case, this is just some mathematical trickery to rewrite this trace into something else. It's advantageous because this something else looks very simple. So this something else becomes the following. So the quantum expectation value of some observable is actually a limit as p goes to infinity of a classical Boltzmann-Wade thermal average of some classical observable instead. So the classical observable is this kind of average over the intermediate positions. And the Hamiltonian, the effective Hamiltonian for the classical replacement system that we're studying, it has the usual potential from before, plus something that looks exactly like springs, basically. So harmonic interactions between neighboring intermediate positions xi. We can interpret this as describing a Hamiltonian of classical beads, so classical point particles connected by springs with Kp stiffness. And these beads connected by springs in a thermal potential have the same statistical mechanics classically that reproduces exactly the quantum mechanical statistical physics. Basically, the classical expectation values as p goes to infinity become exactly the quantum mechanical thermal average. Okay, so we replaced a quantum mechanical system by a classical one. The spring stiffness here has the following dependence on the number on, for example, the mass, the number of beats, and temperature. And this gives us some intuition actually about what is happening. So we replaced a quantum particle by beads connected by springs. And if the temperature is extremely high, the springs are extremely stiff. They would like to pull all the beads together into a single point because they're so much stiffer than any external potential. Meaning that at high temperatures, quantum mechanical particles basically behave as classical point particles in a single point. So this justifies that high temperatures is classical usually. But at low temperatures, the springs become very floppy. The stiffness is very low, and the beads can spread out much more. This describes wave function delocalization at low temperatures. So at low temperatures, we reproduce quantum mechanical effects directly from this. So this gives us an alternative view of what quantum mechanics actually is. We can replace quantum Schrödinger equations with these kinds of classical systems connected by springs, actually. And the potential is the total energy of electrons around the nuclei plus any Coulomb interactions calculated from DFT. Okay, if we have multiple particles, then we just connect neighboring particles in a specific way. So when the two beat indices are the same, they feel the same potential. So statistical mechanics on a quantum particle with a wave function that scales as some exponential, some base, for example, 10 to the 3nth power, is now replaced by statistical mechanics on just 3n times p classical degrees of freedom, so classical particles. This is an exponential speed up in the number of degrees of freedom that we have to consider. And this is the reason why PIMD is nice. So, but there were no approximations here. The only approximation was that P is in practice taken to be a finite value instead of strictly infinity. So this describes all enharmonic effects, everything that's quantum, all entanglement effects, and everything of muons and nuclei. And it's used in quantum chemistry, in DFT codes. It's implemented already in many cases. Okay, so just quickly, we see that in the case of a muon and nitrogen, we see that firstly, it delocalizes a lot. This is the wave function from PIMD. There's no indication of a double potential well. It's just a single potential well. If you plot the spread of the wave function on this diagram, we see that it's actually narrower than any of the other approximations would predict. So due to quantum effects, nitrogens and everything else moves in such a way that the muon becomes more strongly bonded inside an effective potential, if there was such a potential, a single particle potential, than any other approximation would predict. So adiabatic or harmonic approximations. Furthermore, if we look at the actual energy on the x-axis versus the harmonic prediction for the energy, we see that there's basically no correlation between what the actual energy is in quantum mechanics for some configurations, configuration of the muon and nitrogens in a crystal, versus what the harmonic approximation would give us. There's no correlation, meaning that phonon-based methods completely fail in this case. So it's only fully enharmonic, fully multi-particle methods that we must use in this case. There is a hidden silver lining though. If we try to fit these energies though to some effective harmonic multi-particle potential, we can do that. It's just not the harmonic, not the phonon harmonic potential. It's a different kind of potential because the displacements are so large. But that's just more or less a minor point, but it proves that we have no double well here. It's a single potential well that the muon finds itself in. We can also calculate the degree of entanglement, which is another observable that we can do. So it's just basically a correlation averaged over the wave function. And we see that it indicates with distance from the muon, entanglement between the muon and nitrogen, but it starts off at a very high value of about 60% entanglement with the nearest two nitrogens of the muon. So it's definitely not a single particle effect. Okay, and finally, comparison with experiment. We did, so it's all very nice to have calculations that show something, but it would be nice to to say that it's actually relevant in experiment. So we have in this method, quadrupolar level crossing resonance, we have muons coupled to a nucleus, in this case a nitrogen, with spin 1 or more. In an electric field gradient, the nuclear spin levels split. And as we scan the longitudinal field of the muon, we split its Zeeman levels for the muon pointing along or in the opposite direction to the external field. And we get a strong cross-relaxation resonance where the muon can simultaneously fit together with the nitrogen when the condition that the muon Zeeman splitting equals the nuclear level splitting, that we get a resonance there. And this is a unique MUSR technique because it's the only one that's sensitive to charge degrees of freedom, not just magnetic or spin degrees of freedom of the crystal. Okay, this is a short, small schematic. So the muon Zeeman levels split in a magnetic field, and they have strong cross relaxation with the nuclear levels when the two splittings match. These nuclear levels are split because of the electric field gradient inside the crystal. Okay, so we do that by calculating EFGs from DFT. This can be done routinely. We calculate the Hamiltonian for this problem, the QLCR cross-relaxation Hamiltonian, using a modified version of a program, QLCR. And we do that for each of our PIMD runs. We average together all the spin Hamiltonians to get the averaged Hamiltonian projected onto just the spin degrees of freedom of the muon. And then we simulate the QLCR spectrum for such a quantum delocalized muon. This is what we get. At the bottom panel, we see resonance peaks where there's strong cross-relaxation. In the middle panel, we see the time dependence of the muon polarization as a function of time. And in the top panel, a Fourier transform of this. So the frequencies that are in this time dependence. Okay, if we do an experiment, we see that in a certain time window, we get a nice resonance at about 176 Gauss of applied field, plus or minus 1 Gauss. And our quantum prediction gives 175.1 Gauss, which is completely within experimental uncertainty and is 5 times the experimental uncertainty away from the classical prediction without quantum effects of a muon. So one might optimistically interpret this as a 5 sigma confirmation of quantum effects of a muon inside a nitrogen crystal. Because the difference between the classical and quantum predictions is 5 sigma. There is a slight caveat here, though, that there are some experimental normalization issues that have to be tackled very carefully. So there's some extra systematic uncertainty here. But still, it doesn't spoil the main result, basically that quantum predictions match experiment, classical predictions don't. So in conclusion, we've shown that quantum effects of muons can be significant, experimentally relevant as well. And just on basic principles, they should be very strong because the muon is so extremely light and so reactive. It likes to bind to a lot of things in a crystal. Many popular approximations to describe such a quantum muon can and do fail, all the adiabatic and harmonic approximations. But we have a solution that's PET integral molecular dynamics. And I would like to advocate this to anybody that's doing muons, basically. This is something that's now been accepted by the quantum chemistry community as being necessary to describe hydrogen, because otherwise the predictions for a classical hydrogen are completely wrong if you don't take quantum effects into account. For muons, the problem is in principle even more severe. The muon is even more quantum mechanical than hydrogen. So PET integral molecular dynamics looks like it's unavoidable, but it is feasible now thanks to very large supercomputers. Okay, thank you.
Thank you very much, Matthias. I don't know whether you can see. No, not even I can see. Applause sending.
Yeah, I see that.
Ah, you can see it. Okay, thank you.
Thank you.
Okay, I'm sure there are going to be questions to you. So all the participants, please just unmute your microphone and ask a question which you like. So just before the real experts think of any
Mm.
questions, I understand this was not really the essence of your presentation here, but what I really wonder is, how do you get muons into the crystal?
Okay. That is not problematic actually. So it just you have a huge accelerator, a proton accelerator, where the protons impinge on a graphite target. They produce pions there, which then spontaneously decay.
Yes.
Using parity violation effects as well, you get then positive muons that are completely spin polarized, and you get a beam of them. And then you basically just put your crystal inside that beam, and they will get inside a few microns, or well, actually millimeters sometimes. It depends really on the crystal, but yeah, that's not really a problem, yeah, in this case. But you can do more interesting things with this. So when pions decay, they produce muons that are extremely fast. It's a 4.2 MeV, I think, decay or something like that in kinetic energy. You can slow down the muons before you send them to a crystal. So then you can implant them at different depths inside the crystal, depending on the energy that you put for them.
See.
So you can see that depth-dependent studies as well of magnetism.
Very nice, very interesting. Thank you.
Thank you.
So, more questions, please. All you have to do is unmute yourself.
Hi, one question for me. When you talked about path integral molecular dynamics method, you basically represented the quantum particles as a lot of classical particles. So my question is, what is the sensible value of P? So the sensible number of classical particles, so that on one hand you can calculate something in reasonable time, but on the other hand that we get also a good approximation of quantum effects. And is this value like universal for or in some range for every application, or does it vary from use from case to case?
Thank you for the very relevant question. Yes, so it does vary from case to case. So here I have a plot of convergence versus the number of beads in our case. You have to converge it for every case differently, but in our case it's more or less converged with 16 replicas or beads. But it depends really on the temperature that you're using, because temperature squared features in the springs, and that determines the error slightly. So lower temperatures need more beads, and usual values are anything from about 10 beads up to 150 beads, something like that. That's what's usually done. It is somewhat limited though by computational power. So for small molecules, you can do much more beads. This was a relatively large supercell still. But it seems that in terms of the experimental observables that we're interested in, it is converged. You have to converge it for every case though, separately, and for every temperature separately, in principle.
Yeah, okay, makes sense. Yeah, thank you.
Yeah. Thank you.
Thank you. Other questions? So perhaps more for fun than seriously. When will you get in your experimental techniques to the precision when you get into the problems by the fact that the muon magnetic moment is not precisely known?
Well, I mean, I would hope that we'll get there soon, but I don't think we will. Really, I mean,
so it's of the order of 10 to the minus 9, I would say.
10 to the minus 9, yeah, no. So the precision that we have here is so about a Gauss, I guess, in fields of up to a few Teslas. So that's 1 part in 1,000 or 10,000 maybe for fields.
Still a long way to go.
Still a long way, yeah. So we're mostly limited here by the flux, basically, because it's hard to produce a lot of muons. And if you do, it's hard to count all of them correctly as well, due to dead time things of detectors. So yeah, it's hard to get enough statistics sometimes to get to that precision.
Okay, thank you.
Thank you.
I see Professor Kudre unmuted. Lois, you have a question?
Yes. I wondered, a simpler case of the one presented would be some noble gas crystal. Has that already been done, or is it too easy without this molecular interaction?
Yeah.
Or would it give any interesting result at all?
Yeah, okay. Thank you for the question. That is very interesting. I mean, in terms of muons inside crystals, there's really been very few studies up till now. It's just been a few of such molecular cases, actually. In the case here, the motivation was that one thing is experimentally you see strong quantum effects, and also it's expected to get this shallow potential minimum between the two nitrogens. In a noble gas case, you wouldn't get strong bonding, but you might get a very weak potential, basically. So there should be very interesting effects there, like Bloch waves and tunneling, coherent tunneling across such a crystal, I suppose. If the muon doesn't want to bind to anything strongly, it's free to move far away. So yeah, actually, that would be very interesting to study, I think. One would have to look at the specifics if there were any experiments that had any indication of quantum muon effects, because that's where we started, basically looking at which experimental cases were there for quantum muon effects, and this one seemed the most promising. But yeah, it might be interesting to look at it, because I mean, what I neglected here was any effect of tunneling and Bloch waves, but that can also be implemented in PIMD. So you can put the muon on a potential barrier and see how much it likes to spread over it and things like that. So yeah, that's a good idea for a future study. Thank you.
Thank you. Okay, at the moment, I don't see any further questions. So let me just take the opportunity to thank Dr. Gomilšek again. Thank you very much for this nice presentation.
Thank you.
Let me just say for the audience, we don't have a clear program of the near future the department seminars yet. So please stay tuned for notifications over the email and on the web page. Thank you very much for participation, and I hope to see, or well, to at least to hear you very soon again. Thank you very much. Goodbye.
Okay.